So in our today's workshop, intermediate spatial analysis, will continue on our spatial analysis journey. But here we're really going to be focusing now on raster data, whereas last week in basic spatial analysis, our focus was on vector data. Raster data is a little bit different. Obviously, we're generally looking at different types of phenomena than vector data. You can still perform overlay and do all sorts of analysis with raster data. I'd just like to expand your horizons a bit. For those of you who work in the natural sciences, you will almost definitely be working with some sort of raster data because we commonly measure or represent these continuous phenomena across the Earth in a raster format. So things like elevation, temperature, land use, and all sorts of other things are commonly seen as rasters. So we'll take a look at raster data again, how we represent things in raster format in GIS, and then talk about processing and overlay specifically with raster data and how we can simplify our overlay by reclassifying rasters and what that means and how to perform mathematical operations in the raster calculator. We'll examine all those things through what's called a site suitability analysis, which is a very common and fundamental sort of thing you would do in a geographic information system. You're going to analyze a bunch of criteria together to determine if a location is suitable or unsuitable for some purpose or use. We'll also do some other stuff like delineating a watershed. So analyzing a terrain data set or elevation data set to delineate one drainage basin from another. And then also look at interpolation in GIS. So interpolation is where you are estimating values in between sparse data points. So how can you estimate the value of something in between where you actually have data? And so we'll take a look at some tools available to do that sort of operation. So just to review, spatial analysis, what is this? This is where we were examining locations and attributes of our data and the relationships between data sets. And so here, the key takeaways were addressing a question or trying to gain some knowledge. And so the results of our spatial analysis will extract some portion of our data or create new information, often as new data sets out of these operations. So we're combining and analyzing multiple data sets together to address a question. And we took a little bit of a quick look at the spatial analysis workflow, framing our questions, our spatial analysis questions, looking at the scope, exploring our data, how we can use it, the method, identifying suitable methods for answering our problems, and then actually performing the analysis and examining the results. So we'll dive in further to all of these components of the workflow today. Just to remind you again, spatial geoprocessing is this term where we're combining one or more data sets and one or more processing steps together into some workflow to do this analysis. And so the challenge here is determining what is the appropriate workflow and data sets you need to perform your geoprocessing operation. So in this simple example, we might be analyzing elevation data, soil data, and vegetation together. And maybe we want to find areas that are suitable based on some criteria. Our fundamental data sets, elevation, soil, vegetation, have some geoprocessing operations, such as calculating slope, how steep the elevation surface is or the aspect. We may select some subset of our soil or vegetation data and output a new data set for all of these, perform another operation to get our final output. And we'll do an example of this. Lots of examples of this today. So this is our geoprocessing framework of combining data sets and processing steps to answer a question. So as I pointed out last week, we looked all at vector data. And what you may not appreciate before is that vector data can actually model and represent fairly realistic and complicated spatial relationships. So things like containment, overlap between features, directionality, and also chirality or handedness. All these sorts of things can be represented in a vector data model. What that leads to, in a practical sense, is that performing geoprocessing on vector data is usually more computer intensive than on raster data. So oftentimes, if you're running processing on a lot of polygon features, or I should say vector features, it may take a lot of time on your computers here. Any questions on that? So the difference with rasters is that a raster is just a grid of numbers. And computers love to process things on grids of numbers. That's what they were designed to do. So a raster, once again, is this continuous grid of uniformly sized cells. Each of these has a defined coordinate system and potentially a projection to it. And the way these are actually georeferenced is by identifying the coordinates of the upper leftmost cell in that data set. And then from the cell size and the associated coordinate system information, you can determine the location of the center of every other cell in this grid. So the cells are typically square, and you see them in a lot of different formats. We've already seen them in different image formats. They may be Esri grids, BILs, raster geodatabases, lots of possible formats here. So what I want to do first is take a look at some specific raster data in ArcMap and inspect some of the properties of these rasters just to get you familiar with some of the terminology and properties of data in the raster format. So we're going to look at two different rasters that represent elevation here in South Carolina. So each cell represents elevation above sea level. You often see this term digital elevation model, or DEM, referred or used to describe an elevation data set in a raster format. So we'll take a look at two different elevation model files, and we're going to identify and talk about what the format is, pixel type, pixel depth, and some other properties. So I'm going to open my ArcMap document for this session, located in that intermediate spatial analysis folder. It's this intermediate spatial analysis tutorial map document. So I'll double click to open that in ArcMap. If I get a warning about hardware acceleration, remember these machines click no. So we don't want to accelerate the hardware. I'm going to put one of my projectors up, my screen's up here. And when ArcMap pops up, I'll bring it to this screen here so that we can answer or fill out this table for these two raster data sets together. And if you have the PowerPoint open, don't skip ahead where all the answers are already filled in. Maybe I shouldn't have told you the answers are already filled in. But let's take a look at these together once ArcMap opens. All right, so here's my notice about hardware acceleration. I'll click no. And when I open ArcMap, I'm going to notice, just like the last workshop, there's several somethings already loaded or created here in the map. What were those multiple somethings? There are 4 of them. What are my Kraft single American cheese slices called or referring to? What do they represent over here in my table of contents? Data frame. That's the keyword I was looking for. So there's multiple data frames. Just as a reminder, a map document can have multiple data frames. Each one of these is independent of the others. So you can construct a map or multiple maps in the same ArcMap document that operate independently of one another. So what we have already in our data frame, this DEM's data frame, is a data set, this scdem.tiff. And above that in the table of contents is this one, South Carolina DEM, which I'll check the box to turn on and then turn off again. So what are these rasters representing? What property or phenomena? Elevation. Yep. And again, that DEM is a digital elevation model. So these two look fairly similar overall, but have some notable differences. And what we want to do is let's inspect the properties of these and then go back to that table. So let's right-click our scdem.tiff over in our table of contents and then click on properties. And then switch over to the source tab. And the source tells us at the bottom here where the data source is on your machine or on a network or wherever. And then through the top box, it gives us all sorts of information about our raster. And so the answers for our table are going to be located in here. So let me switch back to my my PowerPoint here. I'll open my properties for my raster layer, but I want you guys to help me fill out our table here. So for scdem.tiff, what is the format of our data? A TIFF. What is a TIFF? I mean, it's an image file format. So you often see pictures stored as TIFFs, but it can also represent other things like elevation. What's the pixel type that's listed? Floating point. Okay. Does anybody know what floating point means?
So like a long decimal?
It has the capability to have a decimal in it, unlike an integer, which does not. So there's lots of different ways of representing numbers on a computer. And a floating point format has capability to have a decimal with it. What's the pixel depth that they list in that properties? 32-bit. So the pixel depth describes how many bytes of memory on your machine are used to store a particular number. So this uses 32 bits of information to store every single value in that raster. It also relates to how many numbers you can represent in that format. So the more bits you use, the more numbers you may be able to store. And the general formula is that it's 2 to the n number of digits. And for a 32-bit, let me check my notes. A 32-bit can store generally from -3 to the -38 to 3 to the +38. So very infinitesimally small to incredibly large numbers. Does that make sense? So if the pixel depth was, say, 4-bit, rather than 32, we'd only be able to store 2 to the 4th, which is 64 different numbers. So we can represent more numbers. We're just using more memory on our machine to do it. What's our cell size for that data set? 30 what? 30 meters. How do you know it's meters? We're in UTM. So what's our coordinate system? Clark, yep, Clark 1866 is a datum, and then our projection is UTM zone 17 north. So this is a projected Rasters and universal transverse Mercator projection based on the Clark 1866 data. So it's, what's our vertical units? Is it a trick question? Anybody find it?
Is it not 3D?
Hmm?
Is it vertical elevation?
Yeah, so these are elevation rasters. What's the unit of the values in that raster? Let's see, I'll take a look through my list.
It's good, but it's not listed in the box.
Where do you see foot?
Oh.
Then disregard everything Terry just told.
Yeah, don't listen.
Maybe let's come back to that one in a minute. Let's fill out the table for our South Carolina DEM. So I'll switch over, right click that layer in my table of contents, open the properties, and help me fill out our table again. What's the format of the South Carolina DEM raster?
GDBR.
FGDBR. Yeah, but what is that? File geodatabase raster. So it's a raster within a file geodatabase. That is its one. What's our pixel type and our pixel depth? Signed integers are type. What does that mean? You know what integer means? It's going to be some whole number. Signed means it has a positive or negative associated with it. An unsigned integer only represents positive values. And what was our pixel depth? 16-bit. Yeah, so we're using half the memory on our machine to store each one of these values. And we're only representing elevation as whole numbers, whether they're positive or negative. What's our cell size and coordinate system? $30 what? Where'd you find meters? In the source box this time, right? Because what's our coordinate system and what are the units of that? Yeah, 83 South Carolina state plane. So it's in a state plane projected coordinate system. And what are the vertical units? Don't know. A raster data set doesn't necessarily know what it's representing. So it has to have a defined coordinate system in units for the lateral values, but this vertical unit, we know this is representing elevation, would be in the metadata, or you would know from where you provided it. Or here, let's just take a look at the extents of our data. So our SCDEM went from low about -80 to high 35, 32. Our South Carolina DEM are low, -126, our high 1078. So can anybody guess what they are? Just from the extent.
One speed, one's meters.
One speed, one's meters, which is which?
Meters is the South Carolina and
Yep. And our SCDEM.TIFF is in feet. Or do I have that backwards? No, SCDEM is in feet. It's about a factor of 3.28 between the two. So again, there's also a vertical datum that elevation data are provided in. This is a way of representing elevation values. You would find that in the metadata or from the provider of the raster. So let's see how we did. I'll switch my slide. It may be a bit messy here, but oops. Let's see. Look okay? Pretty much. All right. Questions? All make sense? Good. Okay, some other things that I want to show you with the rasters then. Whoops. Try to take this one back. Let's right-click our SCDEM.TIFF layer. And notice the option to open an attribute table is grayed out, cannot be selected. If I right-click my South Carolina DEM layer, I do have the option to open an attribute table. So go ahead and open that. And I'll drag and drop mine at the bottom. Now it's not quite necessary. I'll just expand it here. What attribute fields do you see in the table? And what do you think they mean? Louder?
Tell you how many cells are at each elevation value.
Right. So this is what's called a value attribute table, or a VAT. The object ID simply is automatically generated, differentiates one cell from another. The value field lists all the unique values in the raster data set, and then the count tells you how many cells have that value. So our values are representing elevations. Notice my negatives, I have just a few cells that represent those. But as I get higher and higher in elevation, I see, for instance, 253 has around 255,000 cells that all take on that value. So our South Carolina DEM, remember, was that signed integer for our pixel height. A value attribute table is only calculated and created for integer rasters. With floating point rasters, there's too many potential values for a value attribute table to be worthwhile. Because we know 0.0000001 or 10 to the -37th is slightly different than 10.1 to the -37th, right? So there's so many potential values in a floating point or decimal raster that it does not calculate a value attribute table. Does that make sense? But we can work with this table and query it just like we could our polygon, or I should say vector layers. For instance, if I wanted to quickly select and highlight those areas that have an elevation between 250 and 500 meters here in South Carolina, I could set up that attribute query by clicking that Select by Attributes button from the table. So I can select by attributes where value, I can double click that word value, is greater than, click my greater than, I can click Get Unique Values to list all of them and find 250. Double click on that. And, so I'll add an and statement, value less than. I can also type a space and put 500. I'll verify my expression to make sure I've typed it in correctly, and then apply. It would help if I had that raster turned on. So now it's highlighted in blue, all of those cells that have an elevation greater than 250 and less than 500. Everybody get that to work? No. Is it possibly an SQL error? So I had value greater than 250 and value less than 500. Good now. If you click it, just click and drag it out. I think you can turn that way. Just weirdness of data, because there aren't that many cells. All right, so we can query our value attribute table just like we can a vector data set. I'll close my selection window. I'm going to clear that selection from my attribute table. Click my clear selection button and then close the table. I'm going to open the South Carolina DEM layer properties and go to the symbology tab. We've worked with vector symbology before for a raster. Our options are a bit different. The default when you add a data set is it's going to stretch, or essentially take a color ramp and then show your data from the low to high values along that color ramp. So we have lots of different color ramps available to us. I'll grab one of these ones near the middle that goes from green through yellow, brown, and white. Is generally used to show elevation, but feel free to experiment here and try different ones. Some other options you could have is a classified color ramp, just like we've seen before when we were mapping quantitative data in our vector data sets. So here we can set up and classify our data using the same methods as we saw before, the default being natural breaks or Jenks method, but we have all those same options available to us. We can change our number of classes and our color ramp and so on. You can also do unique Okay, any questions right now? Everybody feeling pretty good about rasters? Querying value attribute tables? Looks like my screen sharing stopped. Give me a second here. I'm going to try leaving the room and coming back. Seems to work. Okay, I think my screen has come back here. Brian, are you able to see the screen again? All right. So let's talk about raster analysis a little bit. And when we perform some sort of analysis on a raster data set here in a GIS, it does its calculations on a cell-by-cell basis, which makes sense, right? So we can analyze one or many rasters together as long as they have the same cell size and extent. The way it will work is that any operations will run on overlying cells. So here it's not clear whether we're subtracting the middle raster from the top or from the bottom. Nope, from the top. We're adding it to the bottom here. But you can see for each one of these sets of overlying cells, the operation of subtraction will only consider cells that overlay one another. That's what we'd expect to be, I think. And you can form all sorts of different algebra, mathematic operations, logic operations, set algebra, custom functions can all be run. So again, our output values are generally dependent only where cells overlay. But there are some, such as focal functions, they're called, that analyze some neighborhood or group of adjacent cells together. Say if you wanted to smooth your elevation data, you can do a focal statistic function that will take an average of surrounding cells to, say, smooth that input. There are also zonal functions that will analyze all cells with the same value the same way, where a zone indicates all cells that have the same value. So when we analyze our rasters, we're generally just looking down through our set of overlying layers and analyzing overlying cells. When we do overlay, we can do a lot of interesting things when we do our overlay here. As I pointed out, raster overlay is generally much faster than vector overlay operations. When we do overlay, we can do, say, a mathematical combination. We can add or multiply, subtract, and divide our data sets together. We can do Boolean overlays. So we can use some AND function to find multiple criteria in our data sets, do ORs and NOTs. And we can also reclassify rasters to simplify our overlay operations. And we're going to do that today. So, so here on the right, in our upper right corner, we have two different rasters. And let's say we want to overlay these in some sort of suitability problem. Our vegetation has values of 1, 2, or 3 that represent some type of vegetation. Our soils layer has values 23, 24, and 25 that represent some type of soils. Let's say we want to overlay those and look for just those cells that meet some set of our criteria. We could do some AND operation that says I want vegetation code 2 and soil 25. Right? And our output would be down here where it shows ones and zeros, true or false. So anywhere I add both of those true, I return a 1. Anywhere else, I have a 0. And it's false. Everyone with me? Okay, so again, we're going to take multiple raster data sets. And here the example was an AND operation, where I want vegetation to be 2, and I want soil to be 25. These are my suitable areas for whatever my problem is. We can also reclassify our data. Essentially change the values in that data set to simplify the analysis. Here I have 2 vegetation codes that are unsuitable. Let's say I want to ignore or not select the areas of vegetation 1 and 3. I also want to exclude soil type 24 and 23. I can reclassify those unsuitable areas as zeros and keep my suitable areas as 1s. And then if I multiply my rasters, I would get the same output as if I did the AND operation, where anywhere I have a 1 in both of those overlying data sets, I have a 1 retained in my output. Anywhere I have a 0 in either data set, I get a 0. Does that make sense? So 1 and 1 equals 1. 1 times 1 equals 1. There's sort of this analogous, operations between some of our Boolean operators and mathematical operators. The objective of reclassifying is to simplify your input data. If you had 30 classes of land cover and most of them are unsuitable, you could simply say they were all zeros. And all your suitable requests be a 1. And that way you need to have one mathematical operation rather than lots of AND statements or OR statements. Yeah.
When you reclassify like that, are the only options 1, 0, true or false? Okay.
No, so in this example, we're making things 1 and 0, essentially true or false. So we have a totally true or false output. We could also have different values and add them or weight them and multiply them in various ways.
That's why I was wondering, given the multiplication.
Right. So yeah, there's lots of different ways of doing weighted overlay, where we're not just doing 1 and 0, we may have some set of criteria where we have different weighting factors in our model.
It's always been a point of confusion. So if you do that reclassification, so when you go to have an output, you can still show the original data that was related to those reclassifications. So that, like, if you want to show what's being excluded, like a soil type or something like that, then that would still show up on your legend.
The output of reclassification is a new data set. So you haven't deleted or modified your original data. You could still have all of those together in a map. Yep. Any other questions as we're going? All right. So we're going to do some overlay with rasters. We're going to do a site suitability analysis problem for photovoltaic solar panel arrays in South Carolina. We're going to determine if areas are suitable or unsuitable using both a multiplication overlay and a summation overlay or weighted overlay. We're going to use a lot of tools from the Spatial Analyst extension. So if you remember, when we talked about the ARC toolbox, we saw all those different tools within it. Extensions are add-ons to the software. So we at Clemson have a lot of extensions that we've purchased. The Spatial Analyst tools cover a lot of different categories: density analysis, distance, hydrology and groundwater, interpolation, some of these different types, local, neighborhood, and zonal, map algebra, reclassification, raster calculators, solar radiation, and surface tools. And we'll take a look at a lot of those different types today. And hopefully in the LiDAR workshop, we'll take a quick look at the model builder. Within ArcGIS, the model builder is a graphical processing environment where you can build workflows linking different tools and data sets together. So it's a nice way to both document your analysis and automate it. If you want to run the same thing on 100 different data sets, this is a way you can automate that without having to learn any programming language. You can also export those model builder models to Python and run them from the command line if you're interested in that. So here's our first spatial analysis question for today is, where are locations in South Carolina best suited for installation of these PV solar panel arrays? So in this example, I've made up some criteria here, but best is going to be barren or lightly developed areas that are south facing to receive the most sunshine or flat. And in terms of slope, are either gently sloped or flat. Our input data are going to be our South Carolina DEM, so some elevation data, and a land use raster from the NLCD, or the National Land Cover Database. So our first analysis is going to look at just barren land within South Carolina that's south facing and gently sloped. So those are going to be our target areas we want to find. So our method is we're going to use some of these spatial analyst tools. First, the slope tool. Our input is an elevation data set, and our output tells you the slope either as an angle or percent grade for each cell in a raster. So it shows you how steep or flat the ground surface is. We'll use the aspect tool, which tells you the compass direction a cell is facing, if any. We'll reclassify our inputs to simplify our analysis, and then use the Raster calculator, which is just a normal calculator. Right here, we're going to do operations on a set of raster data, or multiple raster data sets. Our workflow, our analysis workflow is going to look something like this. Using our South Carolina DEM, we'll run that slope tool, get an output, run our aspect tool, and that will output a new data set. We're going to reclassify those outputs so that anything with a low slope, say, I forget the exact number off the top of my head, 4% grade or less, it's a low slope. We want those to be a 1. Those are suitable. Steeper slopes are going to be a 0. We'll exclude those. Our aspects, we want south-facing locations. So we'll reclassify those to be a 1. Everything else is 0. And then we'll go to our land cover data and reclassify it so that a barren land is a 1 and everything else is 0. Then we'll multiply through the raster calculator all of these together. And so in our output, we're going to have 1s everywhere we've met all of our criteria and 0s everywhere else. And so this is a Boolean or binary analysis. So we either have suitable or unsuitable. Yes or no, true or false. Does that workflow make sense? Any questions on it? All right, let's give it a shot. Switch over to ArcMap. So I'm going to turn off my SCDEM layer and minimize it here. I'm going to turn on this NLCD SC SP and expand it here in the table of contents. So this is our land cover raster, where the colors represent different land cover types within the state of South Carolina. So we see this one called barren land. That's going to be our suitable areas. So does this look kind of familiar to anyone, at least for these land cover codes? Does anybody remember that tiger bird problem from last week? Like to live in evergreen forests. We were using a version of these data for land cover. So I'll turn off my land cover data set. Start with surface analysis functions. So I'm going to open my search window by hitting Control and F on the keyboard, or by clicking this button at the top to search. And so the first tool we're going to run is that slope tool. So I'll type slope. And I'm looking for the slope spatial analyst tool. So go ahead and click on that. And do you all get an error? What is it telling you? Right, so it's giving you an error that there's no license. So if you leave today and go to run these tools, remember this next step. We need to enable extensions in ArcMap to turn on those tools. So we need to go to our Customize menu at the top and click on Extensions. So my Customize menu at the top, click Extensions, and then I need to check boxes next to the Spatial Analyst. Otherwise, I'll get that message every time I try to run the tools. The reason we don't enable all of these extensions on our machines is that they add startup time. And ArcMap takes long enough to load. We don't need to weigh it down with more extensions. So now if I click my Slope Spatial Analyst tool, I should see my tool dialog open.
You say how to do it again, sorry.
Sure.
My search screen would not come up.
That's all right. To find the tool?
No, I've got the search tool, but like.
Okay, sure. The Customize menu, Extensions, and then check the box next to Spatial Analyst. And click Close. From Customize, Extensions, check next to Spatial Analyst. Okay, the search box can either click the button at the top to search or hit Control and F on the keyboard. All right, so our slope tool needs an input elevation data set. So I'll go to this drop down here for my input raster and say South Carolina DEM. And our output raster, notice the location. It wants to put it, does everybody have the same one? D, Intermediate Spatial Analysis, Results, Geodatabase. All right, so then I can just change the name of it here. I'm going to call it, what am I going to call it? I'll just call it slope. My output measurement type, I'm going to switch from degree to percent rise. So it can output the slope either as an angle or as percent rise, which if you've ever driven in the mountains and seen those signs that say 8% ahead, that means it drops 8 feet for every 100 linear feet traveled, which is the percent rise or the slope. So we're going to analyze things as percent rises or fall. And we can accept our other defaults here, click OK, and run the tool. And it should pop up an ArcMap with a default symbology of applied, where green is areas of low slope and red is areas of higher slope. So we're looking for flat areas in our analysis. Are there any areas that pop right out at you as nice flat areas? Most of the state? Yeah, I mean, there's some nice big areas down here, but I don't think we want to build on those, since these are big inland lakes. But as you zoom in, you get a little more detail from it. So where will we most likely not be building these, at least if we're interested in flat areas? Yeah, up here in the foothills. So here I can see some fairly steep areas up around the top of the state, right? Here's Table Rock, there's Table Rock Reservoir behind it. So I can see those very steep cliff faces. All right, did everybody get that output? No, how many were no's? All right.
Didn't change at all. Give me that there. Like usually, I was just gonna run it again. Now it's giving me an error.
Yeah, it's better when you go over it.
Okay, so give a different name.
We can go to Geoprocessing. Geoprocessing options. Check this box over right here.
Okay.
Click OK.
Now I can try again.
Okay.
Oops.
So here, we did percent rise. Is there anything that was like here? Let's see. Oh, correct. Because of those cells are selected, it don't have red on that. So we can clear that selection up first. Special make sure you turn this layer on, and then selection, clear selection. Clear selected features.
Exactly.
That was okay.
But this is exactly what it is. So it's not two? Okay.
So it's only going to operate on section selected cell.
Okay.
So clear it should operate on.
Okay.
Anybody else have that? P. Remove that. So remember, when you have data selection in the data set, be it math or vector, Remember, we had made a selection in our data, and I cleared that selection because most geoprocessing tools will honor a selection in your data and only calculate on those selected features or cells.
And then after you fix it.
I didn't fix it.
Anything you can suggest?
I would remove it and right-click on it. Click on Geoprocessing. Go to the results. I think it calculated properties. I was trying to
Spatial analysis. Do I have everything? I only need that layer selected.
So it tries to apply default symbologies to data we're already there. It did not update this. The values changed as it went from 0 to 75 because it found that there.
Okay, so I'll get you. Thank you.
All right, so everybody have our slope layer now? All right. So our next one is going to be aspect. So I'll open my search window, hit Control F on the keyboard, or click here in the top of my screen, and I'm searching for aspect from the Spatial Analyst tool set. So our input for this tool is also going to be our South Carolina DEM. So I'll click in my drop down, South Carolina DEM, my output. I'll save that results geodatabase and call it aspect. And I can click OK and run the tool. Yep, we can leave it as planar.
So I can't find stuff on the.
It's not finding it.
Oh, I guess that is.
So considers analyzing the symbology applied shows the expression. Each one of the sounds is easy one. There's a we next to the word here, table of contents are some numeric values. These are the azimuth. Zeroing directly north. So it's splitting up into sectors of about 30 degrees, give or take. So from this data set, we're interested, and notice that it face south, east, or southwest. So I have numeric values from 112.5 up to 247.5. And notice it tells us flat areas are a -1. So now we have our slope, we have our aspect. We need to reclassify our data sets. Right? We're going to simplify our analysis here and reclassify both our slope, our aspect. So let's open our search window. Hit Control F on the keyboard or click this button up here at the top of the screen. And we're going to search for reclassify from the Spatial Analyst toolbox. And I'll expand my tool a bit here. We will, let's see. Let's first do our land use. So our input raster from our drop down is going to be that NLCD SCSP layer, our National Land Cover Database.
Do we need that selected on the table of contents?
No.
No? Okay.
Which one is it?
The NLCD SCSP layer is the reclassify spatial analyst tool. Our reclass field is going to be land cover. This is the one we're going to simplify. Our reclassification scheme is set up through this table where our old values are here on the left and the new values are here on the right. So what we can do is go through our list and we're going to change a barren land to be a 1. That was our suitable area, and everything else to a 0, except for this bottommost layer or entry that says no data. We can leave that as no data. So I'm going to go into open water, and for my new value, type a 0, and do the same for all of these except for barren land, which becomes a 1. And my no data, which will stay as no data. But all the others, I'll type a 0.
I've got the NS subcon. I have the input raster, so I'm not getting that reclassification.
I'll come take a look. And you can save the output as the barren land raster in the results geodatabase. We're in the reclassify. So barren land will become a 1. Everything else will be a 0, except for No, if you want to save this reclassification scheme as a table to use on other data sets, you could save it. You can also load previously set classification. We don't need to save it here. But if you go ahead and click OK, I need to read my output. I'll call this barren or land in my results geodatabase. And then click OK, run my tool, and turn off some of these other rasters. So your color scheme may be slightly different than mine, but here are zones of barren land here in South Carolina. So where does it look like we might have some promising capability to build? Wherever this is, looks like those may be some good spots. But we have some sprinkled throughout the state. Everybody get that data set? Yeah. All right, so let's reclassify our next data set. I'm going to open my reclassify spatial analyst tool again. And let's reclassify our slope layer. So I'll go to my drop down, select slope. And here we're going to reclass the value field. And let's click the classify button. And we're going to reclassify so that, let me check my notes here. Anything up to a 2% rise will be considered flat. So we're going to reclassify and have just two classes, from 0 to 2 and 2 to our maximum of 375. So first, I'm going to set the number of classes to 2. And then change my classification method to manual. And then I can type over here on the right where we have our break values. I can click on one of these and change it. So I want my break value to be 2 to split up my data from 0 to 2 and then 2 to 375. Once I've set that, I can click OK. And now I need to change my new value for that middle class. Change it from a 2 to 0, leaving my old values from 0 to 2 as a new value of 1, and anything that's no data to no data. And I'm going to change the name of my output to slope underscore Boolean. And then I can click OK and run the tool. What did you find? What immediately stands out in our flat areas?
The lakes.
The lakes. Yeah, but we have lots of other areas here within the state that seem to fall into that 0 to 2% slope. Everybody there? All right, well, our next one we'll open our reclassify tool again, and we need to reclassify our aspect. So we could slow down. That's what I was hearing. But this gave me also Yeah, we'll just roll with that one. Your results are good. All right, so we'll reclassify our aspect raster here. So I'll select that from my drop down. Here I'm going to manually type in once again, but I'm going to put a 1 in for the 112.5 to 157.5. Put a 1 in for 157.5 to 202.5. And for 202.5 to 247.5. And everything else will become a 0. And I'll leave my node data as node data. And I'll change my output. I'll call it aspect underscore Boolean. And then I can click OK and run the tool. All right, so here I see, looks like we've got a lot of south-facing area here in the state, but I have my 3 data sets, my barren land, my slope, and aspect that have been reclassified. So now I'm going to use the raster calculator tool to multiply these 3 data sets together. So anything that's a 1 in all 3 of these data sets will be in my output. And anywhere I have a 0 in any of these data sets, it will remain a 0. So I'll go to my search window and type raster calculator from the Spatial Analyst toolset. And here on the left, we have layers. It's reading from the data frame. We can double click to add these to our expression at the bottom and also click on these buttons to build our expression. So we're going to multiply these together. So I'll double click my barren land, click the asterisk for multiply, there it is, times my slope Boolean, times my aspect Boolean. So I have barren land times my slope Boolean times my aspect Boolean. And I'll save my output in the results geodatabase and call it PV Suitability underscore Boolean. And then I can click OK, run that tool, and then we will have our result. So where are we going to build our photovoltaic cells? There are those areas I noticed before. Which are, I don't know where they are in the state. Near Williamsburg, I think that is. Near Lake Marion, looks like we have some flat, or I'm sorry, south-facing, fairly low slope, barren land near Lake Marion and Lake Moultrie. right along the river there. That may be a potential location. But what do you notice overall about our data and our output from our analysis?
There are very few spots that meet the
There's
criteria.
very few spots that meet the criteria. And why are there so few spots?
It's binary.
Because it's binary and we need it to fulfill all of our criteria for it to be suitable. So in a lot of analysis, we may not just want it to be yes or no, have it be Boolean. We may want some sort of weighted analysis or some other combination here where if we frame our analysis slightly differently, we reclassify and have different levels. Say things that are more suitable have a higher value. We reclassify things that are unsuitable, still a 0, and then add them together. We can have a factor anywhere from, in this example, 0 to 6, where 6 would be those areas that we reclassify as low slopes and are south facing and are barren land. Those are still our most desirable areas. But we'll also accept moderate slopes, so something a bit steeper, flat areas, maybe those are just as nice as south facing. And we'll also accept some lightly developed zones as well. So then we're going to output anything that's 0 to 2 means we're still not meeting some of our criteria. From 3 to 5, these are moderately suitable areas. And again, a score of 6 would be our most suitable zones. So just by framing our analysis a bit differently, we can get a different result. So if we were to do this again, let me minimize some of these data sets over here in my table of contents. Turn these off. I'll turn off my base map. Let's retry our analysis, but let's reclassify our data a bit differently. So I'll go to my reclassify tool in the Spatial Analyst toolbox, and let's reclassify our barren land raster, or I'm sorry, our land cover raster. So our NLCD SCSP layer. Where now I have barren land is going to be a 2, but anywhere I have developed open space or developed low intensity, those may also be suitable. So we'll have those as 1s, barren land as a 2, everything else will be a 0. So now I'll save my raster as land cover underscore weighted for a weighted analysis rather than a Boolean. And then click OK to run the tool. So again, I've set I developed open space to 1, developed low intensity 1, barren land to 2, all of 0. So now we open lots of other potential zones that are developed by open space all throughout the state. And we can reclassify again our slope layer. Is everybody with me? All right. Reclassify our slope. Again, I'll go to the classify button there on the right. Change my number of classes, this time to 3. So we're going to have anything from 0 to 2, and then 2 to 4. And I'll set my classification method to manual. So my first break will be 2. I'll replace my 20 with 4, and then leave 375 as my upper break. And then I'll change my values. 0 to 2 will be a 2, 2 to 4 a 1, and 4 to 375 as a 0. And I'll save this output as slope underscore weighted. Click OK. Run the tool. All right, so those lakes still show up prominently as flat features, but now we've got a lot of moderate slopes. And we classify our aspect. So my input aspect will be aspect. I'm going to change, well, actually, just leave this -1 to 0.001 as a 1. That indicates the full area. Change my 112.557.5 to be a 2. 157.5 to 202 as a 2, and 202 to 247 to a 2. And change all the others to a 0. All right, and I'll save my output as aspect underscore weighted. And I'll leave that up there for another few seconds. You can run the tool, and if you want to get ahead, you can run the raster calculator, but add up those outputs rather than multiply them. All right, so I'll click OK, run the tool, get my weighted aspect raster. And now I'll search for the raster calculator. I'll open that tool from my Spatial Analyst toolbox. And here I'm going to add my aspect weighted. So aspect weighted, click the plus sign. Double click my slope weighted layer, click the plus sign, double click my land cover weighted. And I'll save my output now as PV suitability weighted in the results geodatabase. Click OK, run the tool, and then we'll take a look at the output. These layers here, speed up the drawing. So how does it look for us now? Do we have more areas or less than the last one? More, lots more. So we still see these areas that are 6. They're few and far between, but should be the same as from our previous analysis. But now we have this gradation. Or anything that's 0 did not meet any of our criteria. 1s and 2s did not fulfill some of our criteria. 3 through 5 were at least moderately suitable, all the way up to 6, which was our best category here. Everybody get that output? No? I can come around here, but going back to the way we framed the problem and comparing that to before, we have many more areas that are potentially suitable here, and we can now rank them. So there's lots of different ways of framing a problem.
Well, look at the slope of the steps. Here. Here, right? 3. Manual. And
2 and 4. So my first rank is 2.
so 2. Like, numbers that you're moving around. Exactly.
We can use that one. And then we change this one to 2. 2, 4, 1. Slope underscore.
And the other one would be the same, right? Aspect.
Right.
All right.
Did you still keep the south as west as 2, and then did east and west become ones?
Flat. So I need
The flat
negative
became
1 to
ones.
0.
Okay, thank you. And then everything else is just,
Reclassify something differently, or just add it to
because I got another class, I didn't realize of the, what tools is it Raster?
So what's the classifications on that?
Yeah, so these were 1 from 112 to 247 to 2, and the rest of the zeros. Get that in 2, 2, 2. Yep. First one. Yes. The colors will vary from what I have online, but the value came out. So you realize something.
Especially zero.
All right. So here's our result where the symbology just shows those that are moderately suitable and in a bright red. Some very small zones that were most suitable. So we've done some raster overlay now and looked at this one of these classic GIS problems, the site suitability analysis. Any questions on what we did? Comments, observations? Then let's take a break for the next 8 minutes. We'll come back 45 after and take a look at some other geoprocessing tools available to us. All right. Our next example of working with some raster data here, we're going to analyze an elevation data set once again, but here we're going to use some tools to delineate watersheds out of the elevation data. So how many have never heard the term watershed or catchment or drainage? So a watershed or drainage basin is the geographic area where theoretically all precipitation that lands within that zone ends up as flow in the stream draining out of that area. So watersheds or drainage basins are separated by these divides shown by the white line in this graphic, where there's some sort of topographic feature, some topographic high point that acts much like a roof on a house does to separate flow. So precipitation that lands on one side of a roof or within our drainage basin would end up as flow in this stream. Precipitation that falls on the other side of that divide would end up as flow in a different stream. So watersheds are, how many of you are interested in watersheds as some part of your work? I know a few of you are. So when you're looking at, say, restoring a stream, protecting a stream, determining what area contributes flow, you're often not working with geographic or political boundaries. There may be many cities, counties, states, countries, or stakeholders generally that all reside within a particular watershed. So managing a stream generally involves determining who's dumping into that stream or whatever, and so we can delineate these watershed basins to or analyze the topography. Say in hydrologic modeling, we may have a model that uses the average slope of our basin and some runoff prediction model, or lots of other things. So what we're going to do is take a point data set representing USGS stream gauges. We're going to analyze the watersheds associated with each one of these things, or the area contributing flow to every gauge. And so these are things that measure the volumetric flow in the stream. They may have other instruments attached to them that, say, sample the water quality or other parameters. In terms of a GIS, the stream gauges are going to be what are called pour points, where these are the areas, they're the locations for which you're trying to determine that watershed. So what we're going to do is use a number of tools from the Spatial Analyst hydrology tool set. Our input is going to be an elevation data set, and we're going to analyze that. First, we're going to fill it in, which removes imperfections that will affect our watershed delineation later on. Then use the flow direction tool, which is much like our aspect tool, but it shows which direction is downhill, more or less. We'll calculate or accumulate flow. These are areas that have lots of uphill cells. And these, in terms of our model, are areas where streams are likely to be located. Then we will snap our pour points or adjust our locations to areas of high accumulation, and then run the watershed tool, which uses these as inputs. So this is what our workflow looks like. Starting with our South Carolina DEM, we're going to fill in the sinks. Right, this is going to remove closed drainage basins within the model. Then run the flow direction and flow accumulation tools. Snap our stream gauges to our accumulation data set, and then run the watershed tool. I don't think we'll have enough time to calculate the average slope of each one, but within the tutorial, you can review and see how to do that later on. So does that make sense? What we're going to do, again, is take these point locations representing the USGS stream gauges and find what areas of South Carolina actually contribute flow to every one of these. So let's go back to ArcMap here. And I'm going to minimize my DEM's data frame here in the table of contents, and then expand the watershed delineation data frame, and then right-click that watershed delineation data frame and activate it. So these triangles are the locations of these stream gauges that are measuring flow here in streams in South Carolina. We also have this SC Upstate DEM layer that I'll turn on. And I'll expand the drop down here. So this is an elevation data set that's been clipped to this part of South Carolina. So what we'll need to do first is run the fill tool on our DEM. So I'll go to my search window, type in fill, and I'm looking for fill from the Spatial Analyst toolset. And so my input surface raster will be my SC Upstate DEM, and my output I'll call my fill_DEM. And then I can just click OK and run the tool. And this one takes several minutes to calculate. So I probably should have run this step and then sent you all on the break. So we'll just be waiting a minute.
What did you call the output on that?
I called it fill_DEM. Close our bring it back. I don't know if that's all right. So there's my result, which I ran the fill tool from the Spatial Analyst tool set to output this filled DEM. So this has removed any small imperfections in our elevation data set that will cause problems in our watershed delineation later on. ArcMap seems to be frozen for me, so I'll give it a second to catch up. So how many are still waiting for it to finish? How many had it finished already? All right, give it a couple more minutes. There it is. So once your filled DEM is finished, the next thing we're going to run is the flow direction tool. So I'll click open my flow direction. This needs an input surface. We want that input surface to be our filled DEM. And I'll save my output in the results geodatabase as flow_direction. And then I can click OK. So the output is going to look kind of like our aspect tool set here. It's going to have lots of colors, but it will be showing us the downhill direction from each cell.
Is it normal for the first one still to running?
Yeah. I'll run a catch for you. All right, so here are my flow directions. So if I close this and then zoom in, what I'm looking at are different colors which indicate different directions of flow. So really what I have along these lines are a separation in flow. That's probably the edge of some sort of drainage divide, where flow on one side of that boundary would be going into one stream. Water on the other side of the boundary would end up in another stream. So how many are still waiting for the fill to finish? A few. For those that are ready, our next tool is flow accumulation. From our Spatial Analyst tool set. And this will take our flow direction as an input. So my input flow direction raster is here. My output I'll just call flow accumulation in the results geodatabase. I'm going to specify my output as an integer rather than as a floating point. And then I'll click OK. So the output of this tool is going to read through and track cell by cell flow. And the higher the value in each cell, the more upstream cells it has or uphill cells. So anywhere I see a high accumulation, there's a high likelihood that a stream is located there.
With the salt in it.
As we wait for this, I'm I'm going to plug our advanced computing resources here from the Geospatial Center. We've hooked up all these computers in this room and next door, as well as some of the other GIS labs, is this distributed computing cluster. So if you go and do a lot of GIS processing later on and you're constantly waiting for things to finish for, say, an hour or more, there are ways we can discretize your analysis, basically split it all up into chunks, and then run these as individual pieces on all these different computers, and then merge that output together. So we can save a lot of processing time with a little bit of work up front. So we've been using that to, or I've been using that to take LiDAR data and calculate high-resolution DEMs for a lot of South Carolina to help some research projects. So we split up the state into these tiny areas and then send out thousands and thousands of individual processing jobs that finish in an hour or two, rather than waiting for weeks and weeks on a single computer, where your computer will inevitably crash and lose all your results. So just keep that in mind in the future. If you're waiting a long time for things to process, there are other ways of doing it, and we can help you get those up and running. Did Phil finish yet? No. You can click cancel and run the other tools on the DM, just to know how it will be different. If you hadn't removed it, if you overwrote it, it would.
Well, this is the first time I'm saying
What was your input for it? So here, fill.
Is there a way to check that?
Might just watch.
All right, so how many have this flow accumulation? Almost everyone. Okay, so what I'm going to do is just change the symbology here. So I'm going to right click and open the properties for that layer. And I'm going to do a classified symbology with two classes. And I'm going to make it manually classified. And I'm going to have my first break value be 300. Click OK. Click OK. And if I turn off some of my other data sets here and then zoom in, they start to look like streams. So again, all I'm showing is cells that have a large number, at least 300 upstream cells or uphill cells. So these zones of high accumulation are where we would expect streams to be located. Our next processing step, we're going to adjust the locations of our pour points, basically move our stream gauges to zones so that they overlay zones of high accumulation. Because when we run our watershed tool, if we have, I'm trying to find one that's offset somewhat. Let's see what I can find. Here we go. So if I run my watershed tool on this particular point, it is in a zone of low accumulation. Therefore, it's going to think that it has a very small area draining to it. And my watershed will be erroneous. It will end up being about this big rather than representing the true area draining to this cell. So our next step is going to be adjusting this location slightly by bumping it and moving it to a zone of higher accumulation. This is just necessary for a watershed tool to function properly. So how many do not have the flow accumulation yet? Is it processing at least?
Processing.
Okay.
Could you go through that, layer property, which symbology change?
Sure. So I'll double click, open my flow accumulation layer. From the symbology, I select classified. I said yes to compute the histogram. And I set it to 2 classes. And then went to classify and changed my first break value to 300. If you do this on a different data set, that number that you use for a break will depend on your data. I played around with it for a while. It's not necessarily meaningful. It's just makes things show up well in our data. So the next tool we're going to run, I'll go to my search window and type snap pour point. We're going to snap our pour point to these high accumulation zones. So my snap pour point tool, our input raster or feature pour point data is going to be our USGS stream gauges. We can leave the pour point field as object ID. This is just a code which delineates one pour point from another. Our input accumulation raster will be our flow accumulation. And our output, I'll call my stream gauge snap. And my snap distance, this is how far we're going to allow the tool to move our pour point. So we wouldn't want to allow it to move too far because then it may move somewhere that's not representing its true location. But if we type 150, this will allow it to move up to 150 meters, which is still fairly far, but it should snap all of these to a high accumulation cell. So my snap distance is 150. I'll click OK. This one at least goes fairly quickly. And now if I zoom in next to one of these pour points, this bright purple cell is the location of my snapped stream gauge. So it's moved it from here onto this high accumulation zone. The numbers, these are just an ID that read from the object ID. So if this was, this could be an attribute that's meaningful. If there is one in your data set, it could be a name or an ID for that specific stream gauge. Here, it's kind of arbitrary, but it just distinguishes one point from another. So I'll minimize a few things here. The next tool we need to run is the watershed tool, our last one here. So I'll type watershed. And let's see, I want the one from the Spatial Analyst tool set. So I need to go down my list of ways. And our input flow direction raster will just be our flow direction. And our input raster or feature point pour data will be our stream or snapped stream gauges. And I'll save my output in the results geodatabase. I'll change its name to watersheds. And then I'll click OK and run the tool. And the output is going to be a raster where the value of the cell is the same number as the code of my pour point. So I can link the two together. They'll show up with bright colors and be differentiated by that code number.
Which watershed are you?
The Spatial Analyst.
See that. Oh, here.
There's a long list of watershed tools on there. So we input our flow direction. I'll open the tool again. Watershed Spatial Analyst. So my input was my flow direction raster. Whoops, flow direction. My input core point was my snapped stream gauges. And I saved my output just as watersheds in the results geodatabase. So here's my result. Each one of these differently colored zones is that geographic area where any precipitation that falls would ideally end up in a stream and go past one of these stream gauges. And here in my table of contents, do I have it already? No. Yes, I do. There's a layer called these WBD watershed boundaries. These are the quote unquote official watershed boundaries provided in the National Hydrographic Data Set that you can obtain from the USGS. So my input, our pour points are kind of arbitrary, but if you notice the patterns that result just from analyzing our data set to these official boundaries, you see that there is very good agreement between the two. So our results are pretty good. Questions?
I'm missing something on these. Why did it only capture those watersheds?
Because we only calculated drainages for these specific points.
Okay, just for those specific.
Yep.
Okay.
So the pour points for these watersheds are different than the input we specified, but the boundary between these are pretty good, pretty comparable between the two data sets. So if you're interested in delineating drainages for, say, a sensor you've placed in a stream somewhere or a particular part of campus or whatever, you can use this sort of analysis to derive those basins. All right. My mouse is locked up here. So again, if we take it a step further, we can use what's called the zonal statistics tool, get the average slope of each one of these basins, and then output that. And we would have seen here in the upstate, we have high average slopes for these small drainages in the mountains, lower averages slopes as we get closer to the midlands. So another thing I'd like to show you with our Spatial Analyst tool set is how to create contour lines. So if you, say, have an elevation data set, the digital elevation model, you can connect points of equal elevation and generate these contour lines out of it. So our contour lines are another way of showing topography and terrain features. And some analysis methods operate on contour lines, or say for a map, you may want to show contour lines rather than elevation in raster format. So the Spatial Analyst contour tool is very easy to use. We just need to specify our contour interval, or what that spacing is between contours, the starting value, and we can also apply a Z factor. So if our elevation data are in meters, we can output contour lines in feet, vice versa. And we'll take a look at generating contours from two different elevation data sets. So that with a 30-meter resolution and another with a 2-meter resolution, and compare the outputs here. So we have, we'll look at some data here at Clemson, where that covers the Clemson area. One of it is a 30-meter resolution data set, and another is an elevation data set derived from LiDAR with 2-meter resolution. So let's try it out. So I'll go to ArcMap, minimize my watershed delineation data frame, right click on my creating contours data frame and click on activate, and then expand it. So here we have in purple the boundary of Clemson's main campus, and we have our 30-meter resolution DEM, or at least a portion of one cut out. So let's convert this to some contour lines. So from my search bar, I'll search for the contour tool. From the Spatial Analyst toolbox. And my input raster for our first one is going to be this one called the SC Upstate DEM. And I'll save my output. In the results geodatabase, I'll call it contours. Oops. Contours underscore 5 meter underscore upstate. My contour interval will be 5 meters, so I'll type a 5. I'll leave a 0 as my base contour, so it will start drawing lines at 0 meters elevation, and leave my Z factor as 1. My input data are in meters, so I don't need to convert to create my contours. So then I can click OK and run the tool. Click close. And I'll turn off my DEM here. So here are these lines that are now representing topography. Pretty easy, right? So how do our contour lines look? About like you would expect. I see some yes and I see some no. But they look pretty good considering the input data. So let's try this again. I'll switch off these contours and then switch on this layer called Clemson Last to DEM. So this is a digital elevation model derived from LiDAR. It has a much higher resolution. So already between the two data sets, I notice a pretty drastic difference in the way the terrain looks. So let's run that contour tool again. From my Spatial Analyst tool set, but switch my input raster to that Clemson Last to DEM. I'll call these contours underscore 5M underscore LAS. My contour interval will be 5 once again. And I'll leave 0 as my base contour and a Z factor of 1. Then I'll click OK. Click close. And turn off my DEMs and just look at my contour lines. So what do you think? Better or worse than the last ones?
Better.
Much better. Why are they much better?
Resolution.
Yeah, more accurate, better resolution, right? So in my contour lines, I can see the dikes along the lake here show up perfectly. I can see even some small details there in the bottoms. I think I can even see some of these aquaculture fields. So in the LiDAR workshop in a few weeks, we'll show you how to derive the high resolution data that we use to generate our contours. But this is how difficult it is to actually create contours. It's very, very easy to do, but here we have a nice data set that we can work with. The output of these tools has as attributes the value of that contour. So this is the elevation in meters above sea level for each one of these contours. So if I wanted to label them with their contour value, I could do that. Or if I wanted to change the symbology, have say an index contour every 50 meters, I could use that information. But how many think they'll be using the contour tool at some point in their future? A few? Yeah. Awesome. Any questions on it? Other comments? All right. Then the other thing I'd like to show you is interpolation. I'm curious how many think they'd ever want to interpolate data at some point? A few. So interpolation, maybe if I describe it again, we'll point this out. Interpolation is a way of taking some sparsely sampled data, say measuring stations distributed over some area, and then estimating values in between those. So if I have, say, a temperature monitoring station here and another one on the other side of campus, what if I want to estimate the temperature right in between the two? You know, there's different functions or tools that will interpolate or estimate those values using known points. Interpolating, generally speaking, is a complicated topic. It's one that's easy to do in GIS. It's easy to use the tools that interpolate data, but because it's so easy to do, it's very often abused or used incorrectly. So generally speaking, interpolation requires that you understand the distribution of your data very well. So basic summary statistics, is it normal? Is it symmetric? Is it skewed? Is there a relationship between values in space or a covariance of values across space? Is the mean of your data the same everywhere, or is there a trend in your data where things might be increasing or decreasing in one direction or another? Are things that are more similar, or I should say, are things that are close together more similar to one another? Or is there a relationship between variability and how far apart things are in your data? So there's a lot of things you need to understand about your data to use interpolation well. Different interpolation schemes also require different things from your data. So some of them will assume or require that the mean of your data is the same everywhere in space, or that there's some sort of normal or log normal or some other particular distribution. And they may or may not be able to account for trends in your data. So what I will show you today are deterministic interpolation schemes, which mean that these are going to try to fit your data with some simple mathematical formula, or take a very simple averaging of your data to fill in the gaps between them. So they assume very little about your data, but they don't always give very good results. So these are fairly safe to use because you don't need to know a lot about the statistics of your data. So the first one we'll look at is a trend. And so what a trend tries to do is look at the points in your data set, shown here by this surface, and then fit a plane through them. And this plane will show you the general increasing and decreasing directions in your data. So it's an inexact operator, which means it hardly ever fits your data points that were put into it, but it will show you general trends, as the name would imply. Another method I'll show you is what's called inverse distance weighting, or IDW. And this is a method that assumes points that are located near each other are going to be more similar than those that are further away. And that if I estimate the value at an unknown location, it should be some weighted average of the points nearby. And so it's actually going to take a weighted average of your entire data set, but the further away I am from that data point, the less weight I'm going to give that value. So we're fitting or averaging all of our data set at every unknown location, but we'll weight these nearby points most heavily. So you can see all of these very localized peaks and valleys in our weighted surface here. So the more distance we have between our points, the less influence we have on our estimate, or our weighting drops or decreases with the inverse of distance. A spline is another deterministic method that's going to try and fit a curved surface to our data. And it tries to fit the smoothest surface it can. So it's going to minimize derivatives, like the first, second, and third derivatives. So it's trying to fit a very smooth surface through our data. And we could have a regularized or a tension spline. And we'll take a look at those. Questions on any of those methods? No. All right. How many of you have heard of kriging before, or kriging? It's kind of referred to both ways. I'll point it out today because a lot of people use this tool because it gives very nice results and it's easy to check the boxes in ArcGIS, but it actually is a family of interpolation methods. It's an advancement, or a sort of like IDW on steroids here, where we're going to take a weighted average of our data set to interpolate between them. But here we have a weighting factor that looks at the covariance of your data as a function of distance and fits a formula to those, or a relationship. They call it the semi-variogram here. And so we have to actually use a variety of tools to fit all the parts of this curve to our data to properly estimate that weighting factor. And so this is all outside the scope of our workshop here today. So I'll just tell you the main takeaway for today at the bottom is, if you'd like to use kriging, because it's a very, very powerful statistical interpolator here, is that you need to know what you're doing, especially if you're going to present it to, say, a dissertation committee or publish your results somewhere. If you'd like to learn more about kriging, there's a geostatistics course at Clemson. You'll do that for about half the semester and learn all about the different ways of setting up kriging, as well as sampling probability and other cool stuff. Next week, or actually starting tomorrow, we have a workshop on basic spatial statistics if you'd like to learn more about those. This does not get into interpolation, but shows you how to identify clustering within your data, and specifically spatial or statistically significant clustering. So can you apply a hypothesis test and say with 99% certainty that this hotspot of whatever, cancer or lung disease or whatever, is statistically significant, as well as how to do regression of spatial data. So actually fit a model to multiple data sets and predict some value over space. So I encourage you to look into those if you're interested in learning more. Any questions? All right. So what we're going to do is take a look at some temperature data from South Carolina from September 2016 to answer the question, what was the average temperature all across South Carolina for that month and year? And we're going to take these points distributed all over the state and interpolate them a few different ways and inspect the results. So let's switch back to ArcMap. I'm going to minimize my creating contours data frame and activate my interpolation data frame. Oh, yeah. Thank you. Like I said, I have too much stuff on the podium here. It slipped my mind. So activate my interpolation data frame. Go to my SC bookmark so that everything shows up. So these triangular points here, if I open my attribute table, these were weather stations. And what they have is an attribute called T average. So this is the average temperature in degrees Fahrenheit from September 2016. So let's take a look at a few of these different interpolators. The first one we'll do is the trend tool. So I'll open my search window and type trend. And open that from the Spatial Analyst tool set. And the first thing I'm going to do is click down here where it says environments at the bottom. And I'm going to set a processing mask, or basically limit the extent of my output. So I'll click cancel quickly. When I run this tool, it will by default output to a grid defined by the extent of my data set. So it will have values out here beyond South Carolina and out in the ocean. And I just want to restrict my output to this South Carolina border that shows up in black here. So from my trend tool, I'll click on environments here at the bottom, expand this Raster Analysis dropdown. And where it says mask, I'm going to click in the dropdown and specify SC border. And then click OK. And so now my input point features will be my SC temperature data set. My value field is T average. And my output raster I'll save in the results geodatabase, and I'll call it temp_trend. Then I'll just accept the other defaults and click OK. So this is going to fit a linear trend to my data. So you can all click OK. Before I do, which way do you expect there to be a trend in our data? From which direction would we expect to see increasing to decreasing, or decreasing to increasing temperatures?
Coastal mountains, yeah.
Sorry, what?
Increasing at the coast and moving, temperatures decreasing as you move closer to the mountains.
So increasing towards the northwest.
Right, yeah.
Sounds about right. Let's click OK and see what we find. Click close.
Or decreasing towards northwest, right?
Did I say increasing?
Yeah, decreasing.
I did say increasing towards the northwest. Increasing towards the southeast, decreasing towards the northwest. So here's our result. It's a raster where it's classified temperature for us, but it's pretty much exactly like we expected, right? The next thing I'm going to do is click on my bookmarks menu and go to the Clemson bookmark. What I want to do is actually inspect and compare the output estimate of temperature to the actual temperature at a weather station. So I'll go to my Clemson bookmark. I may need to zoom out a bit, I guess. And there's a weather station from Seneca. So I'll click my identify tool here. That blue circle with the letter I, click identify, and then I'll click on that weather station. And it tells me the average temperature was 67.16 degrees. So that was the actual average temperature. I'm going to click then identify from and change that to my temperature trend. And then just start clicking around the weather station and take a look at the values. So what do you find? Did we estimate the actual value pretty closely or not? So our actual temperature was 67.1. Our result was about 64.4. So the range of our data is about 7 degrees, so we're not really fitting it that well. But then I'll click and close my identify tool, go back to my SC bookmark. The next one we'll try, the next interpolator is the IDW. So let's see how this inverse distance weighting looks when we use that to interpolate. So I'll search for IDW in my search bar. And we want the IDW from the Spatial Analyst toolset. And so our input point features will be our SC temperature, our value field T average, and I'll save my output as temp underscore IDW. And I will leave all the other defaults, but I'm going to set that analysis mask again. So I'll go to my environments, click on Raster Analysis, and set my mask to the SC border. Click OK again, and run the tool. So how does this look?
More accurate.
More accurate. Yep. So here we actually see high and low zones, especially. I don't know what this part of the state is called. I can't remember. Any South Carolina people help me out?
PD.
The PD? Okay. So here I had a weather station. That had an average temperature of 53 degrees. Not that far from one that was averaging almost 71 degrees. Pretty interesting. But I noticed that I have these localized zones, these sort of bullseye looking features around every data point. Because again, my weighting of the point is an inverse of the distance. So as I get further and further away from this point, I'm not using or weighting that one very heavily. And so this point over here has a very, very tiny weighting factor for that point. So I have something that shows a lot more detail and variability in my data, but each one of these estimated measurements is very strongly influenced by the points closest to it. So let's compare our output, our estimate, to the actual measurement back up there in Clemson. So we'll go to my bookmarks, click Clemson. May need to zoom out or move over a bit. And I'll click my identify tool. And I want to identify from my temp IDW layer.
Where's the identify tool? I'm sorry.
That's that blue circle with the letter I. So the identify from was here at the top. Temp IDW. So as I look right around that weather station, what was the estimate that you get?
So mine has never changed. When I changed to the IDW, say, same.
Stayed the same as it was from the trend?
It did. No.
Really?
I got it. I got it.
Oh,
Yeah.
Oh, okay. So how close was it to our weather station in terms of the values? My weather station, again, was 67.16 degrees. From my IDW, I get almost exactly that, which you would expect because the only value I have nearby is that weather station. So the further I get from it, the more I'm going to notice a change. All right, so let's try that spline tool next. I'll switch my bookmarks again, go to my search bar and search for a spline from my Spatial Analyst tool set. So my input point features, my SC temperature, my value field is T average. And I'll save my output as temp_spline. I'll accept the other defaults, but I'll set that raster analysis mask one more time by going to environments, raster analysis, and then set my mask to be SC border. And then I'll click OK, and then click OK and run the tool. So how does this one look? It shows the same general trends as we saw in our IDW, that we have this localized lower temperature and higher temperature here in the PD, sort of higher zone down here. Now, again, what we've done is we've fit a three-dimensional surface through our points, or attempted to fit a surface through our points that minimizes the curvature as much as possible to make it as smooth as possible. So let's compare this output to our weather station. I'll go to my Clemson bookmark, find my weather station here, and I will identify now for my temperature spline layer. And I get something that's fairly close, within 1/2 of a degree or better, right around that weather station. So what we did was just take a look at a few different deterministic interpolators, right? Don't really require much out of our data, but we're now estimating values at all these unknown locations using some set of known values here. So this could be temperature, it could be chemical concentration, could be a variety of different things. We looked at our fitting a trend, fitting a spline, and the inverse distance weighting. Questions on any of those? All right. Then we can finish a little early today. Whoops. This one is offset. So for our workshop series, this bar got adjusted. We're almost halfway through them at this point. Like I said, this Friday and next Thursday, we're going to do a session on basic spatial statistics. That's pretty neat. The following one is field data collection. So we're going to use some apps on our phones or tablets to go out and map things out in the field, and also learn, we'll learn 2 different apps, one called Collector that works on a phone or tablet, or Survey 123, which can be run from a browser to go out and do field data collection. The following week, we'll look at 3D LiDAR point cloud data, how to bring those into GIS and use them in analysis workflows. Then we have an intro to ArcGIS Online, so using the browser-based cloud version of the software for mapping and analysis and create these cool things called story maps. We'll have a session introducing Tableau, which is a data analytics software. And then finally, a session on using drones and terrestrial laser scanning to create map data. So thank you for attending. Please fill out the survey before you leave today. I'll send out a link for the tutorial data recording of this session. Thank you all for coming. Let me know if you have any questions. Enjoy the rest of your week. Go out and practice some GIS. All right.